Okay, Alejandro. You can start, Alejandro. Do you want to do a little intro
Yep.
before?
I'm ready. So I shared my window here. Wait a minute.
Oh, we lost the display.
Now it's okay.
It's coming up, yes. Okay.
There it is.
Yeah, we can see.
Great. Well, thank you very much for the invitation. When Laura told me about giving this talk, I was surprised and also very delightful about telling you about these things. I have been working many years. And well, the basic ideas are a bit old, almost 20 years ago. And well, for an introduction, Defeasible Logic Programming, that we say DLP or in Spanish DLP, is a formalization of defeasible reasoning. It takes idea from logic programming and argumentation and combine them. It deals with tentative and contradictory information. Conclusions are supported by arguments, and it performs an exhaustive analysis of all the related arguments that are involved, and it's possible to give a detailed explanation or answer. I will start with the syntax of the language, and I give you both definition of an example. A divisible logic program is a set of divisible rules and strict rules and facts. A divisible rules is not, as you are seeing there, where both the head and the body of the rules have literals and represent a weaker connection between pieces of information. For example, a divisible rule with head H and body B express the reason to believe in the body is a divisible reason to believe in the head. There are some examples there. I'm going to give, this example is going to be the whole presentation, so don't be afraid of forgetting something now. For example, the rule waves implies nice represent a reason to believe that there are big waves is a reason to believe that it should be a nice days for surfing. In this connection is weak because there might be other reasons that will lead to the contrary conclusion. For example, the other rule that says normally if it is raining, is it not nice for surfing? Literals in the head or body of a rule can use a strong negation symbol. For instance, they are nice and not nice are complementary or contradictory literals. Then we have strict rules that only differ in the connection symbol and represent a strong connection between pieces of information. Here there are examples. If you are on vacation, you are not working. If there are not many surfers, there are few surfers. If you are ill, you don't surf. And finally, you have facts that are ground literals and used for representing information that is considered to hold in the application domain. For example, here, the facts are that it's Monday, it's cloudy, we are in the dry season, there are waves, the grass has grown, you hire a gardener, and you are on vacation. And there are another divisible rules in the example that we are going to use later. Then, the first step, if the divisible derivation, a ground literal has a divisible derivation if there is a finite sequence of ground literals where each literal is a fact, or there exists a rule, strict or divisible, with head, Li, and body, so that every element in the body is an element that is already appearing in the sequence preceding it. For instance, rain has the derivation rain and cloudy. Usually I use this light blue background to denote the rules I'm talking about in the example. And L has a strict derivation in contrast to divisible derivation if the derivation only use strict rules or facts. For example, not working has a strict derivation. And we assume that no pair of contradictory literals can be strictly derived from any program. However, it is possible to obtain a divisible derivation for contradictory literals from a program. For example, both rain and not rain have a divisible derivation. In the presence of divisible derivation for contradictory literals, a dialectical process will decide which information prevails. I will play this process soon, and conclusions will be supported by arguments, which are structures based on divisible derivations. An argument is a set of divisible rules where there is a strict derivation, a divisible derivation for the conclusion. The set of the argument is not contradictory with the strict part of the program, and there is no proper subset of the argument that satisfies 1 and 2. That is, an argument provides the derivation that is not contradictory and is minimal. Here we have an example of an argument for the conclusion self that use 4 divisible rules. And I'm going to introduce this graphical representation for arguments and subarguments because it will be easy to show the other definition later. So here the argument A is represented as a triangle. In the top vertex you see the conclusion of the argument, and inside the triangle we have the subarguments that are parts of subsets of the arguments. There, the argument for self has 2 subarguments, one that its conclusion is nice, and the other that the conclusion is not busy. Then, given 2 arguments, the arguments can be related. For example, the first relation I'm going to introduce is the disagreement relation. Here we have 2 arguments. One, the one I showed you before for self, and now another argument that its conclusion is that the weather is not nice. And this new argument, the yellow triangle that is denoted with the letter L, disagree with a subargument of the first argument because they both have a contradictory conclusion. Then when we have an argument that disagree with a subargument of another argument, we have a counter-argument. In this case, the yellow argument is a counter-argument for the blue one, the subargument N, and also a counter-argument for the argument for self. So every counter-argument for an argument is also a counter-argument for every super-argument, or all the arguments that contain these disagreements of argument. The argument N is called the disagreement subargument of the relation. Are you hearing me well?
Yeah. So can I ask a quick question? So there is no
Yeah.
equivalent of negation as failure in your system.
I exclude negation as failure from this presentation. It's going to be too long, but
Okay.
in the language we have negation. I can answer this question at the end.
Okay, sure.
But it is you have it. But Laura said to me that I have 30 or 40 minutes, so I had to decide the minimal presentation as I can. Sorry about that.
Fair enough. Fair enough.
So once you define the counter argument, then we can define this notion of defeater. A defeater is a counter argument that is preferred to the argument or not comparable to the argument. So first you have the disagreement relation. With the disagreement relation, we have the counter-argument relation. Then you need a preference relation among arguments, and with preference relation and counter-argument relation, we define this defeat relation. So a counter-argument that is preferred to the disagreement subargument is a proper defeater, and when the counter-argument is not comparable to the disagreement subargument, then it's a blocking defeater. In this case, this argument L is a blocking defeater for the subargument N, and also a blocking defeater for the argument A. Regarding preference, any partial order among arguments can be used as a preference criterion. We decide to have the preference modular, so for any different application domain, you can have a preference criterion among arguments that is suitable for that domain. For instance, you can have priority among rules, or specificity, or priority among evidence, or also priority among informants that give you the rules, or also if you want, certain factors can also be used for preference. Then here in the example, there are more rules. For instance, there is an argument that the conclusion is it's not going to rain because we are in the dry season. And here I introduce a preference among rules. I have these two rules, R1 that support rain and R2 that support no rain. And I assume that the rule R2 is have a priority over the rule R1. So in this domain, I have these rule priorities, and the rule that we are in the dry season will be preferred over the other rule. So using this preference among rules, you can define a preference among arguments, and now we have a proper defeaters, because the argument R is a counter-argument for the argument X, and R has a rule that is better than the other one, so R is a proper defeater for X. What I wanted to to show in this example, I did it on purpose, is that attacks or counter-argument and defeaters can apply to the conclusion of the argument itself, or also an inner point. Here, on purpose, I having a defeater L that is attacking an inner point of the argument sorry, and this proper defeater R that is attacking an inner point of the argument L. So defeaters can attack the conclusion of another argument or an inner point. Both are okay. And defeater can be proper when they are preferred to the attacking argument, or blocking if no preference is present there. Okay? Too many definitions to consume. Sorry about that. Now I will show you how this dialectical process works. Sorry. To compute an answer for a query, DLP begins by constructing an argument that supports C. So having an argument for C means you can have a defeasible derivation for C that is not contradictory with the strict knowledge and also minimal. Then the dialectical process searches for all possible defeaters for that argument, and if there exist, all the possible defeaters for the defeaters, and so on. So a structure that we call dialectical tree is obtained, where every node in this tree, with the exception of the root, of course, is a defeater of his parent. Then we have a marking process that assigns a D or a new, D for defeated and U for undefeated, to every node in the tree. Every leaf is marked U because it's undefeated. Leaves has no defeater, so they are undefeated. And every internal node can be marked D or U. D, defeated when have at least one child mark U, or inner nodes are marking U if all his children are marked D. Here I have an example where there is one inner node that is marked U, is the one at the right, and the other inner node are marked D. Once we have this marking process, we arrive to the main notion, that is, a conclusion is warrant from a DLP program if there exists at least one dialectical tree for an argument that supports C, and the root for this tree is marked U. This is so because you can have more than an argument that has C as a conclusion. In my example, there was only one argument because I had to maintain it in one slide, the example. But you can have for the same conclusion several arguments, and each argument is a potential warrant for this conclusion if you have at least one dialectical tree that has the root mark U, then you have a warrant for this conclusion. And also you have the tree, all the tree provides you an explanation of all the internal process that involves looking for arguments and defeaters for defeaters. Every path from the root to a leaf we call argumentation line. And I introduce this notion now because in the electrical trees, we need that all the argumentation lines are acceptables. And acceptable means that we have to avoid this kind of problematic situations. For example, in the left part, you have an argument B that is defeated by M, and then B is reintroduced as a defeater for M, and then M is introduced again, and then you have an infinite line that we must avoid. And also this other circular situation that involves argument A, B, and C, that A defeats C, C defeats B, and B defeats A. So this other situation also can lead to an infinite line. So in order to avoid this problematic situation, we have this definition of acceptable argumentation line. Argumentation line is acceptable if no arguments appears more than once in a line, and also a subargument of a disagreement subargument cannot appear again. And we divide in every argumentation line, we separate supporting argument from interference arguments. Supporting arguments are those arguments that are in favor of the main conclusion. For example, in this line, the argument H0 is supporting H0, and the argument A1 is interference with that conclusion, but the argument A2 that is defeating A1 is defending the acceptance of the conclusion H0. So arguments A3 is defeating A2, so if interference, and argument A4 is defending indirectly A0. So the arguments in blue are supporting arguments for the main conclusion, and the arguments in yellow are interference with the acceptance of the main argument. So in argumentation line, to be acceptable, the set of supporting arguments should be not contradictory among themselves, and the same for the interference argument. Then having a dialectical tree where every argumentation line there is acceptable, the answer for a query C from a program P will be in the LP as yes if the conclusion is warranted from P. Here there is an example. You have two arguments for C and at least one dialectical tree that has his root mark U. The answer can be no in the case that the complement of C is warrant. Here you have an example when there are two arguments for C and one argument for the contrary, not C, and there is a warrant for not C. So the answer for the query C will be no. And then we have the answer unknown to capture the situation when C is not in the signature of the program. And finally, the answer undecided for those cases where you have not warrant for C nor the complement not C. And as I told you before, dialectical trees provide an explanation for the whole process we did. Then returning to our application example, we have now another counter-argument for the main one, that is a defeater for the subargument T that support that you cannot go surfing because you are busy, because the grass has grown and you have work to do, then you will be busy. And then we have this defeater that say that since you hire a gardener, then you don't have to work on your yard. So this is a defeater for being busy. So now we can mark this dialectical tree, and the root of the tree is U. So now we have a warrant for the conclusion of the argument A, that is, you have reasons to believe in going surfing. And the answer will be yes. And the whole tree gives you a detailed explanation for the answer, because you have first you have the argument that support surf, because it is nice and you have spare time, because you are not busy, because you are not working, because you are on vacation. You have these two defeaters that is cloudy, so it's not nice, and the grass has grown, so you will be busy, but both defeaters are in turn defeated, because being in dry season is a reason supporting that it's not going to rain, and since you hire the gardener, then you have reasons to believe you don't have to work. So you have a whole explanation supporting the answer yes. In summary, DLP, all the conclusions are supported by arguments. Perform an exhaustive analysis of all related arguments. The preference between arguments can be adapted to the application domain because it's modular. It allows representing tentative information and also representing potentially conflicting information, and it's possible to give a detailed explanation for the answers. And that's all. Thank you very much. And for 30 minutes, what I was trying to do. I leave there some query codes for these two papers and another video that I made for my classes that has more details about the whole dialectical process for your reference.
Thank you. Are there any questions for Alejandro? Yeah, Michael?
Be unmuted. Thanks. That was a great presentation. It was very clear and gave the answers that I was looking for. So thank you. But I do have a couple of questions, or maybe there's one question with perhaps an elaboration of what Gopal was asking earlier. So I'm trying to figure out why you use the phrase that you're doing argumentation in logic programming. Where is the logic programming part of this? And to me, it seems to me there are two parts that could be included. One would be negationist failure, but you mentioned that you have, at least in the presentation, not mentioned that. The other was that your rules are rules. In other words, they're directional. If you have L0 implies L1, you do not have not L1 implies not L0. They go in one direction and not in the other direction. And then, of course, you've also added independently, which is not logic programming, but you've added these preferences. But logic programming features that I would have imagined there was one was the possibility of negationist failure, which you didn't mention. The second is the fact that the rules are directional. Is there any other aspect of logic programming as opposed to general logic that is important in what you're doing?
Well, I start talking about the rules. When we start working on this project, we wanted to have this dialectical process for having argument and counter arguments, and we decided to use the language of logic programming, that the rules, also all the ideas about variables in logic programming. There are schemes. I use here an example with propositional letters or propositional atoms, but you can have variables, and you use variables in the same sense as logic programming. There are schemes that you can instantiate with atoms. So variables are possible, and the rules, the strict rules, are very similar to logic programming rules, the strict ones, and also facts. And they are not implications, as you say. They are one direction. So we have no contrapositives there. And we differentiate the defeasible rules from strict rules just for a representation things. So node representation is a very important part here. You should decide for your knowledge how to represent it. Maybe in one domain the rule should be strict, and in another domain should be defeasible. Is a representation problem. Maybe in a general example, the rule can be strict, but in a more detailed one, it should be defeasible. For example, you can have a strict rule that you say if the traffic light is red, you should stop. You can represent it as a strict rule, and maybe it's okay. But usually, if you are in an emergency, you don't pay attention of traffic light. So in this new domain that you want to represent this emergency situation, you can say that at a red light, you should stop as defeasible rule, and then in an emergency, you have a red light and you don't stop. But you can also use a third rule that say, if you are in an emergency and there is a red light, but it's danger, do not cross, because another car is approaching, or a heavy traffic, or so on. So on one hand, you have the decision how to represent your knowledge. I avoid to mention, when Laura said to me 30 minutes, I had to make very big decisions, and the difficult part was, as always, the things I had to give to put outside the presentation. So I wanted you to see an example, a practical example, not just letters. And that's my agenda was showing you an example, showing you the main definition that are defeasible derivation, argument, counter-argument defeater, and then showing you in a graphical form all the whole process, not with a formal definition, because it's too much for 30 minutes. Usually when I give you a more detailed talk, I need at least 4 hours, so it's a lot, really a lot. Usually I give when I give a class in an undergraduate course, I teach this, and I used to spend 2 classes of 2 hours to give a more detailed view. Regarding the rules, we also introduce in DLP the possibility of having defeasible rules with no body. So they are not facts, because in logic programming, a rule with no body is a fact. So they are all rules. You have rules with head and body, or only head that are queries, and only body that are facts. In DLP, a defeasible rule with no body is not a fact. We call them a presumption. That is something you presume to be true, but it's not as true as a fact. So you can use them but you have to be very precisely with the definition. So I included from the today talk. And also you can have negation of failure. But here, when we start introducing, we were thinking about having negation of failure here, and we start making examples in the first part of our research, we understand that failure is not an illogic programming. In logic programming, you have derivation, and the failure is the derivation that fails. But here, the definition we give for negation of failure is that the warrant fails, not the derivation. So if the derivation fails, you have no argument. But you can have an argument, but it's defeated, and you have no warrant for it. So here, negation of failure is the failure of the warrant. So the system, when found a negation of failure, not looks for a derivation for the literal. So if it has not C, the semantic is not the failure of the derivation of C, is the failure of the warrant of C. So you have to look for a warrant for C. So that's possible, and that's the yeah.
Now that means then that negation as failure isn't embeddable. It's a global, sort of only at the top level of this reasoning do you have failure, because you can't, you don't have the ability to say whether an argument is valid or not as a condition to something, or warranted as a condition of something. All makes perfect sense. By the way, I'd also like to say it was a great talk with a great presentation, and I thought you did an absolutely excellent job of choosing good thing, what we needed to know. Anyway, it was wonderful. Thank you so much.
So if can I ask a question? So if I have a definition of P and I have another definition for not P, then I must give a preference rule preferring one over the other.
Not necessary. It's something that is how is the word? Is something that is I'm missing the word. It's not necessary if you have a preference. It's not difference in different levels.
But it then means you couldn't use that alone as in a warranted argument, right?
Such a contradiction was excluded by assumption. Excuse me.
No, that's only strict. That's strict.
For strict rules. This was excluded by assumption. My question was that it may be quite difficult to find whether such a contradiction do not hold.
Oh, sorry.
It's undecidable, of course, if with variables.
Yeah. Sorry, before continue, I can't remember your name. Geneseret. I saying okay, Geneseret.
Yes.
Your last name.
Michael.
Michael. I can't remember your name. Sorry. Michael, all your questions were answered. I can't remember all of them.
Sorry.
No,
yes, you did answer the question.
I was missing something. No, okay. No, because there were a lot of questions that were all related, and I tried to give a single answer relating all of them, but I can't remember if all of them were answered.
Yes,
And
yes.
then
I apologize because I did kind of conflate several issues there, but you did get to it. The main thing had to do with the fact that it's a rule rather than just a disjunction or an contrapositive.
Yes.
But I did have another question. The other question, as it was on your talk, I didn't understand the distinction between unknown and undecided. Is there?
It's not very important, that distinction. I make that distinction because it's not very important. And the important thing is, as David Warren say a bit before, you can have a warrant for a conclusion that you are sure that you have this dialectical tree supporting you. You can have a warrant for the contrary, then you can say no, but with a solid argument. No? In logic programming, you say yes when you have derivation, and you say no for everything else. And here you say yes when you have a solid argument that is warranted from your analysis, or you say no when you have an argument for the contrary. Then you have to show the contrary for saying no. You cannot say no because you don't know. And then you have an undecided situation when you cannot say yes, definitely yes, or definitely no, because you have an argument for the contrary. Then you have these undecided situations, and I wanted to differentiate an undecided situation where you have analyzed a lot of information and you are undecided because you have arguments in favor and argument against, and you have a lot of argument and analysis. And then there is this unknown situation when you have no information at all. It's something that you don't know nothing. So it's not in the signature of the program. So it's something that you never thought about before. So it's a special case of the undecided situation that is a no. But usually this is my opinion. It's good to have this distinction to understand when you have an analysis or you don't know nothing at all. And the question that Cobalt asked about these preference rules, having preference among rules is an easy way to show you comparing arguments. Maybe the easiest way. So you say the program is formed with rules. Then if you can compare the rules, and as you notice, I'm not applying numbers to rules. I'm just saying I have a partial order among rules. So I have this rule in this domain. This rule is better than the other rule. Maybe because that rule is more informal, or maybe it's because an expert told you about that, or maybe your experience in life is that this rule apply better to this domain, whatever. So from comparing rules, you can make a definition for comparing arguments. Our basic way of comparing arguments is the following. If you have an argument A and an argument B, and the argument A has at least one rule that is better than another rule in argument B, and the contrary does not happen, that is, there is no other rule in B that is better in A, then argument A is preferred over argument B. To avoid this situation when you have a blocking situation among rules in two different arguments. But if you have, so having preference avoid undecided situation, as David said. So if you want to have at the least undecided situation, then you have to have a preference among arguments and, for instance, preference among rules. But we have also produced a definition of preference among arguments that try to capture specificity among arguments that is completely syntactical. That is, the definition is tricky, so maybe you have to read it from the paper, because we wanted to have a syntactic preference, because the comparison rules is a semantic or pragmatical way of thinking. So you are putting there the representation of the knowledge of the problem. And also you can have, for instance, each rule can be something that an informant tell to the agent. So imagining a multi-agent environment. So each agent represents the knowledge with a DLP program and share knowledge. And we were working with this, making dialogues. Agents can dialogue among them, sharing knowledge with defeasible rules or almost program. And so each agent can assign to the information that received from another agent, the agent, how is the agent that send the knowledge, not the receiver. The country of receiver is the emitter, no, is the sender. So each rule can have the informant, and then you can compare the arguments accounting the informant. So more information provide you better information, and then you prefer those arguments over the rest. So that's another possibility we have been studying.
Thank you. Paul, there's a question? Or who?
Yeah, I have a so great talk, by the way. I have a question related to the logic, the possibly logical semantics of argument A defeats argument B. So far, it's like a primitive relation that doesn't have a clear alignment with logic. We know it's a partial order and maybe it shouldn't have cycles in it, and that's about it. But it would be interesting, I don't know if you did some work on that, to see if there is a logical foundation of A defeats B that's kind of meaningful. An example would be finding a contradiction in B. If A in some sense does that, then based on that it defeats B, or finding opposite factual information, or finding a fault interpretation of statistics, because most of those things are statistical, and of course they can be interpreted wrongly. Did you elaborate a bit about what A defeats B means in terms of a logical foundation?
No, this is a good idea, Paul. We didn't study this relation from a logical viewpoint. We were working in different areas, because here, as you notice, there are like the different levels. You have the representation level when you have to decide which rules you are going to have in your program, and how we are going to compare the rules or the argument. Then you have the other level, that is how arguments are related, and then you have this other process that make the exhaustive process of making the answer for the program. So there are different levels, and also there is another level that is a more strategical level, that how you look for the answer because of the computational problem that you have there. Also there is a strategical view there, and then we have also been studying how to use in a single agent reasoning system, and also in a multi-agent reasoning system, sharing knowledge. That there are many things to do there, because you can have many agent reasoning over the same problem, that is sharing arguments, building this dialectical tree in a cooperative way. And also you can have agents that they are discussing and just giving the reason in dialectical trees, in a dialogue. But we haven't studied, Paul, the underlying logic about this relation. That would be nice to do that. The thing that I remember when I started studying this several years ago, I remember that we try to avoid to have self-defeating arguments. This is because we have this contradictory condition in the definition of arguments. So arguments cannot contradict themselves. And also we were studying if proper defeaters can defeat themselves, and it is possible, because since defeater attack the conclusion or the inner part, you can have two defeaters that attack an inner part, and also they are proper defeaters of themselves. Maybe doing research on the logic there can give more answers about the semantical view.
Yeah,
In
and
some sense,
that's maybe very interesting in your context, is that generative AI, you can program agents to generate different opinions, depending on the prompt that you use. And that would be very interesting in a multi-agent configuration, how you could use your logic to clarify and eventually monitor, make a monitoring agent for those multi-agent LLMs with different opinions. And it's a big problem that people are facing in using multi-agent generative AI. So that would be a possibly very interesting venue, because the operation that is primitive, A defends B, can be a matter of belief, or can be an oracle agent that states it, that's coming from a stronger LLM or something like that. Do you think that could be a continuation of this work line?
I completely agree. I completely agree with that, Paul, because last week we were talking with a colleague here that we work together, and we were talking about exactly that maybe we can provide some clarification for that kind of reasoning that is nowadays very obscure, how it's done. I don't know if the word obscure is okay in English. In Spanish, it's perfect. It's something that you don't understand exactly. It's like thinking in the darkness, and maybe we have something to collaborate there, and provide a way of understanding if the reason is going well, or going in some direction at least. No, I completely agree.
I guess the problem there would be to make sure that the facts to begin with are reliable.
Yeah, that's Veronica, is a representation problem that we always face. That's because we introduce these presumptions to have the possibility of representing things that you are at least in the domain you are representing, because you have to always think that you are representing an abstraction of the world you are dealing with. So if you consider that something is a fact, then it's okay to represent as a fact. If you are not sure, then you have to represent it as a presumption, and then the system will treat them differently, both of them.
Yeah, what I mean is that with LLMs, very often, in most cases, you're not going to be sure. If they produce a program for you, you can at least check the program because you know how to program. But if you're getting facts on which opinions are elaborated, and you're not sure of the facts, which you're never with an LLM, that's a very slippery terrain. You can reason on that all you like, but it's still slippery.
Yeah.
So the assumptions are identified syntactically that this is an assumption rather than a fact or something?
Yes, we call them presumption just for not using that term that was used for another thing. A presumption is a defeasible root with no body. So it's like a defeasible fact in some sense.
Right. So so sort of you already, it'd just be like a defeasible rule with true as its body.
Yeah.
So it's the same.
Yeah.
It's exactly.
A
So you've
defeasible
already
rule with true.
incorporated into your
Yeah, we
system.
have incorporated them because I mentioned at the beginning that we are assuming that the strict part of the program is not contradictory. So you cannot have contradicts themselves, and also you cannot have a strict derivation for contradictory conclusion. So the strict part should be safe in some sense, no contradiction. But if you have one, as Veronica said, if you have one LLM that say you something and then say the contrary, on another one say the contrary, then you can introduce in the program as two presumptions. Contradictory presumptions are okay, not a problem. Then maybe you have an undecided situation. If you had, I don't know, the universe is infinite, and then the universe is not infinite, then the situation is undecided, unless you have a preference over one or the other presumption.
How do you check that it is not contradictory for the strict rules?
Well, in a theoretical viewpoint, we assume it, but we in the implementation we did, we just check that for the strict part that you cannot derive two contradictory literals, just to be sure, because the problem is that since an argument should be not contradictory, if you have a contradictory part, the strict part, the pi with the letter pi, if it is contradictory, then every argument will be contradictory because if using it. So we have to avoid that. And in practical terms, you have to check it not to be sure that arguments are well constructed. In theoretical terms, we assume it. So we assuming that the trick part is not contradictory.
Can you check this efficiently?
No, it's not efficient there. We were working more in the theoretical part than in the efficient, part. So no, it's very naive, the implementation we have.
Because it seems that there is an extreme search space, and that there are some that there must be possibly some useful syntactic conditions that should substantially help in such search.
Yeah.
And another question is, do I assume that it is rather easily to be implemented in Prolog?
Yeah, yes. My first implementation was in Prolog. I love Prolog. It's
So
the
only
language
the first one?
I use it most. If someone asks me what is your favorite language, Prolog, no doubt, is the one I use more, and the ones I love more. Is clearly it's beautiful. Prolog is beautiful. I'm not objective in this. I cannot be objective about this. It's easy. Sorry, uh, how I pronounce your name? Wodek.
Wodek, yes, indeed.
Wodek. Sorry, Wodek. I correct you. It's not very easy. It's easier than in other language because there are some parts that are very easy. Derivation is easy. Also, the dialectical process is easy because you can implement it with negation and failure very easy, and also gives you something that is very nice, that you can how to say, prune the tree for unnecessary branches. Because once you understand that the root is D, for example, then you don't need to continue, and the implementation in Prolog is great for that. But for other things like this contradictory check, and also the minimality check of arguments, and another the comparison criteria, and then it's easy but not very easy. But
the propositional case is decidable either directly with a fixed point or with ASP.
Yeah.
But otherwise, I would say tabling in Prolog can help to detect things like circularities, because you probably don't want circular rules either in the ones that are not contradictory.
Yes, I have to admit the following. In the beginning, when I started working on this, I very fan of implementation, and I put a lot of time implementing. But nowadays, and I have so many obligations, so I had to admit that implementations, it was in the past. So it's very difficult to find time to do implementation, and I'm now more concerned to theoretical expansion of this, and we are applying it to making decision, for example, in a multi-agent environment, how agent can use argumentation for support the decisions, and also for instance, now we are working on a concept that is not an argument itself. That is, usually humans do not share complete arguments. They share incomplete arguments because they assume that the other people for example, here I assume a lot of things you know. You know a lot of things of logic and logic programming and computer science. They assuming that, then when I talking, I'm not giving you the complete explanation or argument for everything I said. And that has a word that is entimeme. When you talk, you use entimeme, that is incomplete arguments. Now we are working on a project of doing argumentation with incomplete arguments, with empty memes. And also, we have a student has finished the last month his PhD and trying to extract argument from text. So not to produce the arguments completely by coding them, that is very exhausting, but trying to extract directly argument from text, so we can do argumentation with information that we can collect. But talking now with you, I refresh my programming side. I would like to continue programming with your ideas, but I love product. It's maybe the best language I know.
Okay, so I think maybe we're beyond the hour, so maybe
Okay,
we
I
thank
have one more.
Alejandro and
Yeah, I have one more question, but everybody can leave because it's kind of very specialized for Alejandro. If you can stay a few minutes, Alejandro, can you?
so should I
Yes.
stop the recording and then
Well, thank you very much, people, for being interested in all this stuff.
Thank you. That
My
was
apology to being so short in the presentation.
No,
oh no, it was wonderful.
yeah, it was
Thank you very much.
great. Yes, thank
I
you.
We
appreciate
can
it.
call you again, Alejandro.
Thank
We
you.
can call you again.
Thanks.
Thank you.
Thank you. Thank you.
Yeah, thank you.
Thank you very much. Thank you very much
You all, thank you.
for all your questions.